Hello, everyone. My name is Yadong Li. I'm a principal engineer from Intel, working on Intel SmartNIC and IPU architecture. With me today is Ziyan. Ziyan worked on SPDK NVMe over TCP Initiator design and has done a lot of performance optimizations for SPDK as well. And so today our presentation is going to talk about Intel Mount Evans IPU-based NVMe over TCP Initiator offload. Okay, so I'm going to request. So here's a quick overview of today's agenda. First, we will do a brief introduction of IPU, and then we will do a quick intro of Intel Mount Evans IPU, focus on the NVMe interface and the NVMe over TCP Initiator design. We will talk a lot about the SPDK design details for NVMe over TCP Initiator design, and also talk about performance evaluation for the SPDK NVMe over TCP Initiator using Intel Ethernet 800 series with application device queues. And then we have a quick summary. So here's a brief introduction of IPU. First, IPU stands for Infrastructure Processing Unit. Is an evaluation of Smart NICs, provides full infrastructure offload. IPU provides highly intelligent infrastructure acceleration. It minimizes latency and jitters, maximizes revenue from host CPU. It also provides a system-level security solution, provides separation of infrastructure and a tenant. CSP can fully have control for the infrastructure application software running inside IPU, and the tenant can have full control over the application and the business logic running on the host CPU. IPU is highly programmable, built to customer needs, enable CSPs to do the innovations in the cloud pace. In this topic, we will briefly introduce Intel's ASIC-based IPU Mount Evans, and then describe NVMe over TCP Initiator implementation as an example for IPU-based storage offload. So here is a quick intro of Intel Mount Evans IPU. Some of you may see this one from Intel Architecture Day announcement and the Hard Chips Mount Evans presentation from last month. Mount Evans is Intel's high performance 200 gig IPU, pure ASIC-based design. It's co-designed with a top cloud provider, hyperscale ready, integrates a lot of links from multiple generations of SmartNIC based on FPGA and IPUs. It delivers high performance under real-world workloads, provides security and isolation from ground up. There are a few technologies we want to highlight in this product. First, it provides a highly programmable packet processing engine, which can support very advanced vSwitch and other networking applications. It also comes with a high performance NVMe storage interface design. We basically take Intel Optane SD IP, right? So we basically take the NVMe protocol processing IP from Intel Optane SD product line and optimize for IPU, scale it up for cloud use case. It also has this next generation reliable transport, which solves issues for the RDMA in a large scale out cloud deployment environments, delivers reliable performance and consistent performance in cloud scale. It provides advanced crypto and compression accelerator engines for security offload and for storage use case. As for software, we want to highlight a couple of things. So we provide P4 Studio based on Barefoot, P4 SDE, which makes packet processing pipeline programmability much easier and enable customers to do customizations on top of the P4 vSwitch pipelines. we leverage and extend the DPDK and SPDK. So today we will talk a lot about the SPDK for NVMe over TCP initiator design. So a little bit more information about this NVMe interface. We designed this product for cloud use case, and we can support multi-host as well. So here we support connection to 4 Xeon host. It implements SRV, supports large number of VFs. We also support large number of namespaces. Each namespace can support data at rest crypto. It has an advanced quality of service solution which can provide IOPS and bandwidth limiting. One product engine we want also to mention here is this look-aside crypto and the compression engine, which is based on Intel Quick Assist Technology Q80 IP. LCE can be used for crypto compression and CRC offloads. It supports chained operation, so which is very useful for storage data flows we're talking about today. The other thing to note here is Manavins also support PCIe load ports, which can be used for attaching SSD directly to Manavins. So before we talk about the NVMe over TCP initiator design, I just want to do a quick refresh of the typical scale-out storage architecture. So this picture is highly simplified, which shows a typical storage management orchestration framework, right? A control plane, which is going to manage storage targets and also configure initiator to access remote storage. So first to note, inside IPU, we can support different storage protocols. Our architecture is flexible, is based on SPD framework. So here we state a few protocols. We can support NVMe over TCP, NVMe over RDMA, integration with self backend protocols, or just bring your own storage solutions, right? So it's very flexible. So a typical orchestration flow is the control plane, talk to target and create a new virtual storage volume. For example, create one SSD with 250 gigabytes capacity, right? So once the storage volume is ready, the control plane comes in the initiator, in this case, talk to the IPU to say, I need a new virtual SSD, create a new virtual NVMe device, and then the software running on the IP will configure internal NVMe interface. For example, configure the VF, configure number of queues, attach the namespace to the NVMe function, right? And then the namespace can be scanned by the NVMe driver running on a host. So the storage volume now is ready for applications running on the host to use. So that's the typical flow. Inside the IPU, we talk about the NVMe hardware interface. In previous slides, we basically support this NVMe protocol processing IP has advanced quality of service, load balancing logic. And we talk about crypto offload, compression offload, and the CRC offload in the IPU hardware path itself. So, so this is a quick high-level overview. Going to next level, here we're going to focus on NVMe over TCP today. So here's a next level view how this NVMe over TCP data path looks like, right? In IPU. So the right picture is a highly simplified picture, but basically on the host, the standard NVMe driver sees a real NVMe device function, right? It can be NVMe PF or NVMe VF. When NVMe driver posts the commands to NVMe device interface, the NVMe hardware interface, in this case, this is an NVMe protocol initiator, in short, MPI. This is the hardware interface that we talked about in previous slides, right? Process the commands, fetch the commands from the host, do the necessary processing, and then forward the commands to the SOC inside IPU. So the software now can take over, process the commands, and use this LCE Q80 IP to do, different offload operations. In this, for example, it can be used for crypto offload, CRC offload, right? We mentioned about the chain operation. So you can, when you do the DMA from Xeon host to local SOC, you can do crypto plus CRC, right? In the same operation. If the storage protocol can support the compression at the initiator, you can do chain operation, for example, compress crypto and the CRC as well. So, so this LCE Q80 is very useful for building a very efficient storage data processing flow. From a software point of view, the IPU software here for NVMe are fully integrated with SPDK NVMe over Fabric soft stack. We highlighted one software component here. This is the MPI transport, right? So at the concept level, it's similar to TCP transport and the RDMA transport integrated with the NVMe over Fabric layer, NVF layer. We call this MPI transport. It's not a real networking transport, but is a local device interface transport integrated with NVF layer, and it can talk to the device driver for any NVMe internal device configuration and for commands processing. So once this MPI transport is in place, it enables a large software use from SPDK, and we go through the BDEV layer and the NVMe over TCP initiator, and SPDK comes with different solutions, which Zian will talk in next few slides, right? And so it provides a very flexible framework for implementing different initiator. So, so basically, this is a quick intro of MyNavins and the NVMe over TCP initiator solution based on MyNavins. So next, we can go into the details of SPDK design. So Zian, please take over.
In this section, we will talk about the following topics. Firstly, we will have a quick overview related with SPDK and especially the MNE over Fabrics related components. Then we will have a detailed introduction of SPDK's use space MNE over TCP Initiator design. And last, we will share how SPDK MNE over TCP Initiator can utilize the ADQ feature in Intel's E800 series NIC. So this page just shows the SPDK architecture, especially related with MNE over Fabrics. We can see that SPDK builds its own MNE over Fabrics target solution, and it utilizes the MNE over Fabrics layer, and also the block device abstraction layer. And last, it just utilizes the different implementations related with MNE. For example, we support TCP transport, RDMA transport, and PCIe transport. And especially for Intel's IPU storage initiator software, we just use this the components highlighted in this diagram. It is MNE over Fabrics target, the MNE over Fabrics layer, and MNE BDEV layer, especially with TCP transport implementation. And this page just describes the detailed information in SPDK project, how we implement the complicated TCP initiator stack in SPDK library. We can see that firstly, we create SPDK MNE BDEV, and it relies on SPDK's user-based MNE driver. And this MNE driver has several transport. We abstract it and generate the common functions and port details in each transport. we can see that we currently support 3 kinds of transport. And in Intel's IPU, we use the TCP transport. And for the TCP transport, we rely on SPDK's socket implementation library. It composes of different socket implementations. They are POSIX and the ULIN. Especially the ULIN implementation still uses a kernel TCP IP stack, but it relies on the new features in Linux kernel named ULIN, and there is a libULIN library in the USpace, and it is async programming. It provides async programming mode, and it can be used to continually efficiently use the kernel stack. And this is available in relatively new Linux kernel. And this page just has a very brief introduction of the ADQ feature, application device queues feature in Intel's Ethernet 800 series. Actually, we have a brief introduction last year. ADQ is an open technology designed to improve application-specific queuing and steering. And the ADQ, the core of the ADQ technology is that it can filter application traffic to a dedicated and isolated set of queues in NIC. Then applications threads execution are connected to those allocated specific queues within the ADQ technology. Then the application can get the benefit by the kernel have the bandwidth control of application TX network traffic. And with the ADQ technology, the application can finally have the following benefit. For example, we can increase application predictability and also reduce application latency and improve applications throughput. So this is a very innovative technique provided by Intel Ethernet 800 series NIC. In this page, we will describe how ADQ is enabled in SPDK socket layer. And naturally, if you do not modify any SPDK's code, we can still integrate ADQ technology, but we cannot fully explore the capability of the ADQ. So to better leverage the ADQ technology, we can do the following support in SPDK's socket library. The first is the common support for both server and client side. It means that this technique can be used for both MNE over Fabric's TCP target and host. And in socket layer, we implement a function to get an API ID for the socket file descriptors owned by the application. Actually, the API ID represents the hardware queues. Then the application can know which socket is created on which hardware queue. So then we can utilize this information to design a very good packet dispatching among different CPUs. For example, last year, we shared how ADQ can improve the performance for SPDK's MNE over Fabric's TCP target. Actually, in the server side, we use the NAPI ID to implement a NAPI ID-based scheduling algorithm. It means with the NAPI ID information, we can dispatch the MNE or TCP connections with the same NAPI ID info in the socket related with socket file descriptor to dispatch the same SPDK thread. then it will benefit the target with the multiple CPU core configuration. It means that with this smart NIC ID based scheduling, we can always find optimal socket polling groups for each MNUR fabric TCP connection. Then we can eliminate the resource contention among multiple CPU cores. It means that the MNUR fabric TCP connections or the socket-file descriptors with the same NIC ID info will always be handled by the same CPU core. So with this solution, we can fully explore the ADQ capability. But we know that if we do this for the initiator side, especially for MN over TCP initiator side, we cannot do this because we know that from the initiator side, socket is already created on a dedicated SPDK thread on the initiator side. So we cannot directly use the same methodology on the server side. For example, to seek and optimize the socket polling group and schedule the socket into it. This is not the good solution, because if we do that, we need to leverage SPDK's thread send message functions among different SPDK threads to conduct the socket I/O operations, and there is additional performance penalty. Then we get the performance benefit from ADQ, but we have the additional performance penalty. So this will not be the good solution. So to address this issue, we propose another solution. The solution is that we will leverage NIC ID and the SUMAC optnames on the socket together, and the purpose is to enforce all the sockets in the same polling group to set with the same SUMAC value. Then in Linux kernel, we can schedule those sockets with the same SUMAC value with on the same hardware queue managed by the ADQ technology. Then we can continue benefit the performance improvement through the ADQ technology. And in next page, we will share the details how we do it. This page just shows when the MNUR Fabrics initiator creates a socket on a dedicated thread and how we can manage it if we enable the ADQ technology. For example, through the diagram, you can see that if we want to create a socket A, we will firstly get a valid value through the NIC ID optname and save this as the placement ID. And we need to maintain a global list named L with the placement ID, group info reference structures inside this list. And when this socket A will be added to a group G, and we first check whether the placement mark-based strategy, it is related ADQ, is enabled or not. If it's not enabled, we can just add this socket A into the group G. So this is easy. If it's enabled, we need to check whether the socket polling group has a valid placement ID or not. If we do not have a valid placement ID, we need to initialize the placement ID of the group. We will choose an unused placement ID from the list L. And secondly, we will update the SUMAC information of the socket A with the same value from the group G. And then we will try to update all the socket in group G with the same SUMAC info. Then we will finally add socket A into group G. If the group G's placement ID is valid. So this is easy. Then we will just need to update the SmartNIC info of the socket A and then add it. Then we can still schedule and use a group-based scheduling or the group-based IO handling algorithm for NVMe over TCP Initiator, and we can still have the benefit by the ADQ technology. So yeah, now is your turn.
Okay, so we're going to talk about SPDK NVMe over TCP Initiator performance evaluation. This is using publicly available Intel 100 gig product, Intel Ethernet 800 series with application device queues technology. Last year, we shared performance in the presentation optimizing user space NVMe over TCP transport solutions, right? So that performance data was from target side, and today we're sharing the performance from the initiator side. But again, just to be very clear, this is from Intel Ethernet 800 series publicly available. So don't be confused by the first portion of discussion on Manavis, because for Manavis, at this time we cannot disclose any performance yet. So so just keep it in that mind, right? So everything here we are talking about is for this Intel 100 gig product line, which is publicly available Intel Ethernet 800 series. So here's the test topology. It's basically a very simple setup. We have two Xeon hosts connected back to back using this Intel Ethernet network adapter E810. Both run SPDK. The left host here is running the initiator test, right? So so we show the NVMe over TCP initiator here in the user space, and we use FIO as the application for test purpose. The TCP IP networking stack running in the kernel. On the target side, it's run same SPDK stack, but it uses for the NVMe over TCP target. And one thing to note here is we have 6 Optane SSDs. This is code stream SSDs. Okay, so this is a very simple view of this back-to-back test configuration using Intel Ethernet network adapter E810. So the performance we're going to show you is the performance data from the initiator, which is from the system on the left side of this picture. So here's the performance slide. Okay, this slide has 2 sets of data on the IOPS and the average latency. The IOPS I displayed in the box here. So the light blue color one is the baseline SPDK NVMe over TCP initiator, right? And the dark blue one is with ADQ enabled. The lines here are for average latency. Again, the dark blue line is for ADQ enabled. The lower the better in this case for latency. So we're going to show you a few data points, right? So if I look at the one core test from IOPS point of view with ADQ enabled, it shows 28%. I mean IOPS increase. So that's a very big number there, and the latency shows about 23% reduction. And at 11 cores tests, an ADQ saturates 100 gig pipe with about 2.85 milliamps, and it shows 32% throughput increase compared to the baseline data, right? At the same time, it can still show 23% latency reduction. So this is a very significant improvement. So at more cores, like 12 cores, it still shows notable throughput increase, like more than 20% here, right? Even, I mean, the baseline number is getting better because of more cores. So the short summary here is with ADQ enabled SPDK NVMe over TCP initiator shows, I mean, very significant performance improved in both IOPS and latency reduction. So this data, just to be clear, this is from 4K IO read test. Default networking setting is 1500 bytes MTU, and the FIO test 2, right, using QDEPS32, and is a random read. Again, the remote target system has Optane drives, so it gives me enough IOPS to saturate this 100 gig pipe. And ADQ shows notable performance improvement here. One of the key value of ADQ is reduce jitters, reduce tail latency, right? So the next chart here shows that basically performance improvement. So here we're showing two data points here, right? Basically, again, so we have 4 lines here. The dark blue lines are for the ADQ latency number. Here we're basically choosing 2 nines and 4 nines just to give you a view of how much ADQ can help reduce tail latency. The light color one is the baseline SPDK. So at the 1 core data point here, if I look at 4 nines tail latency with ADQ enabled, right, it shows 16% of tail latency reduction, which is also a big number. And with more cores, more IOPS, the improvement, right, from ADQ is more obvious. So in this case, on the 12 cores test, with 4 nines tail latency, ADQ can reduce 43% of tail latency. So this is again, so it's very impressive improvement with ADQ enabled. So again, this data is from Intel Ethernet network adapter E810 series. So here comes to our summary here. Today we talk about the IPU management, right? So IPU provides efficient infrastructure offload, improves data center efficiency. It's designed to help minimize the latency, jitter, maximize revenue from host CPU. In this session, we shared Intel management IPU-based NVMe over TCP Initiator offload. We talk about integration with SPDK NVMe over TCP Initiator, and we showed test with Intel Ethernet 800 series network adapter, and with ADQ enabled, it shows significant performance improvement for SPDK NVMe over TCP Initiator. Finally, we welcome any SPDK optimizations and enhancements to make it best for IPU storage solutions. So we have test configuration in the backup, and we just encourage you to take a look at some of the detailed configuration of the system and the ADQ configuration. So it's easier to understand the test configuration we have. Okay, so this is basically our presentation today. We thank you for listening, and we welcome any SPDK optimizations and enhancements to make it the best for IP storage solutions.